So we're looking at the following homework question that you had on polar coordinates. So we want to first plot this -4, -π3. When you're plotting polar coordinates, the first thing you want to do is move in the direction that your angle is. So this is -π3. So going to the pole, you're going to go downwards π3. Once you've gotten to that angle, so this line at that angle, you want to go either up or down depending on what this angle is. So our value is -4, and so we're going to go in the opposite direction, and so we're going to go 4 upwards. So this looks like 4 here, this A. Since this is on my math lab, or you have a choice ABC, we want to just make sure these other ones don't work. This is +π3, that's not working. This is too big, so none of those are right, so this would be A. Okay. And so the next question says, what are the coordinates of the point where R is bigger than 0 and your angle is between -2π and 0? So we want to figure out the same point that we could get right here if our value was bigger than 0 and this was a negative angle. So we're going to have to get up into the second quadrant, and we want to go negative, so we're going to go clockwise. We know our reference angle down here, that was the π3. So we're going to take pi plus π3, so that's 3π3 plus π3, that's 4π3. But we're going clockwise, so that's going to be a -4π3. We wanted R to be positive. So we're going to have 4, 4π3. Oops. Rewrite the point as it satisfies this differential. So π3 plus 3π3, that's right. Let's see what they have. Maybe that space. Type the ordered pair, type the exact using pi. Use integers or fractions or numbers expression. Let's just see what it says. Oh, duh. And you guys might have been chatting, maybe not. Didn't I say that had to be a negative angle? Okay. Anyway, so,
yeah.
but I didn't put it there. You guys do that too? I'm sure you do. So here I could do a similar exercise if I wanted to get rid of that. But this is, we know what we're doing. So what is the coordinate of the point for which R is less than 0 and that your angle is between 0 and 2π? So now our angle is going to be a positive angle. And so here we're going to be sweeping up here. So this is going to be, well, think of it here as pi minus π3. So that's going to be a 2π3. Let me just make sure I'm doing all of this right. But R is less than 0. Actually, no. So if R is less than 0, we're going to have to come down over here. And so if we look at 2π minus π3, that would give us the positive angle this way. So 2π minus π3, that's 2π, that's 6π minus π3, that's 5π3. Okay, so we wanted a positive angle, but a negative R to get up there. So this would be -4, comma, 5π3. Oops. And I see I did that wrong. Okay, so you're just following the directions where you're getting another point, polar point, that's going to give you to the same exact point as this one. Just remember that if your R value is negative, it has to go across that line to the I guess the one that's diagonal across whatever that line is, the opposite direction. So I'm going to end there. I don't really need to save it. Then I wanted to show you real quick. We weren't gonna, I decided not to get into 8.2 or that you guys have to do homework, but I want you to just get a kind of an idea of what these graphs look like when you graph in polar coordinates. So last night I found this cool feature on my math lab. So let me just pull that up for you guys.
Excuse me, Professor.
Yeah.
So on the previous problem, do we just add pi to the y value?
It really depends on if you're doing positive or negatives, right? Which direction, what their value of 2 pi they want, that theta. I'd have to look at what the directions were and figure it out through there. Sometimes, yeah, adding pi would help. Sometimes subtracting pi would help. I would first figure out which quadrant you are, what your point is, and then figure out what that reference angle is, and then determine, you know, is it wanting me to get a negative angle, so I'm going clockwise, how am I going to get there? Or does it want me to go a positive angle, am I going counterclockwise? And what is that reference angle, depending on which quadrant I am, to figure that out. But you're right, I think pi a lot of times is going to get you to the exact opposite of that line, or subtract pi. Okay, so I'm trying to share this, and I need to get this into a different tab. So I'm in my math lab, and so over here, and I'm actually in the instructor, so let me go back to what I believe you guys would see more. Here you have a video and resource library that has a lot of cool different tools. This is where you could find the last, in the back of each chapter, they do the exercises for the test, and they have little videos on that. You can watch any videos on the sections, so you can go in here, you can pull up the textbook. So I'm going to do polar coordinates. I want to do 10.2. Oops, wrong place. So this right here, it pulls it up for some reason for all the sections. This is what I was talking about, the chapter test prep videos. So for exercise 1, it's going to show you all these and go through a video of each problem. Okay, I believe. Sorry. Okay, so graphing polar coordinates, you can get these really cool shapes. You can get hearts, you can get flowers, you can get lines, circles, and they have some different names. And so remember R was equal to the length that we went out. And so up here, you see R is equal to A. And so,
Zaja, go ask her why.
okay, so it depends on what A is. It depends on how far you would go out. So let's play this. And A right now is 3. Oops. Yeah, sorry. So I'm looping around here, and all the values of 3, at every value, the angle was not defined here, you're going to get a circle. So if I change that A value then it would go out further. So if I go to 10, it's a circle centered at 0, 0, radius 10. If my A value R equals a negative, let's do this, negative 7. It's still a circle at radius 7, centered at 0, 0. Okay, so let's look at a different graph. So that's if you just have R equals a number. If you have R equals theta, well, theta is how far you're going to go up. So if theta was pi 4, you're going up here. And so it didn't tell us what R is. So any point on this theta would be a point on the graph, which would be a line. So let's look at that. R equals theta. Actually, maybe I'm wrong. Oh, this is R equals theta. I'm sorry, I looked at this different. I thought it was theta equals a number. R equals theta, your R value, how far you're going out, and your theta value are exactly the same. So you're not going 0, you're not moving any direction, and your Y value is not changing. And so here we have a point at 0, 0. At like pi 4ths, your Y value is also going to be pi 4ths. And so you get this spiral shaping graph as you sweep across and plot points as you're going on this graph. And depending on what A is, depends on how far. I think maybe. So again, you're sweeping out and you're going to get this spiral shape in here. It's going a little slow, but basically, again, you're plotting all your theta values, and theta value is the same value as your Y value. So R equals A sine B theta. Actually, that's actually, I think we have horizontal lines and vertical lines. And I'm wrong again. Okay, so this A value, this is the number that's out front of your sign, and B value is part of the argument. So the value of B actually gives us how many petals this graph has. Let me blow it up. Let me make A a little bigger. So A is 10 here. Notice this is actually a radius of 10 in here. Those petals are a length of 10. The B value, how many petals we're going to have. So when it was odd, I noticed that you have the same number of petals. So when I have B is 1, I have 1 petal. When B was 2, I have, this is the multiple. If it's an even argument, that B value is even, then it looked like I always had double that. So here was 2, so I had 4. And it has to do with symmetry. Okay. So 3, that's an odd number, 3 petals. 4, I'm going to have 8 petals. 5, so you get these kind of cool daisy shapes, what I think of them looking like. Okay. So instead, if it was A times cosine of B theta, kind of the similar graphs. We can get these kind of, to me, look like star. Actually, those actually look like those petals too. So you have this app on here, and so you can play along with it, around with it, but you get these, like I said, you can get these really cool shapes as you're graphing them. So we're not going to have time to really go through and graph these, but again, it has to do with symmetry, and it has to do with your R value. We can find our R value depending on our equation and what your theta value is, how much you're swiping, and get points. Okay. So right now you do have homework scheduled for 10.2. Just go ahead and skip it. If you have it done, I'll give you extra credit, but don't worry about that. Don't do that for extra credit. Worry more about the other stuff. So we're going to jump into 10.3, which is complex planes and Moivre's theorem. And this is kind of some cool stuff. So just let's recall real quick what a complex number is, and then let's look at the graph of a complex number. And then we're going to convert complex numbers into polar form. So I'm going to rotate my screen. Hopefully everything works out fine. Okay, so recall, complex numbers can be in the form of z equals x plus iy. I always think of it a little bit differently, but that's okay. This is how they write it, and this is how you'll see it. So in this form, x is equal to the real part, and the y value is equal to the imaginary part. So graphing complex numbers, basically it looks like the rectangular coordinates. The x-axis represents your real number, and the y-axis represents the imaginary number. So this is our real axis, imaginary part. So if they wanted us to plot, or z is equal to, I don't know, 2 plus 3i. Okay, so our real part is 2, our imaginary part is 3. And so we would fall, for this problem, we would fall in quadrant 1. And so you would go over the real part, 2, and then because it's positive, we're going to go up 3. And so we get a point right here. So notice this. We can form a triangle. We're getting good at this, right?
Professor, could you scroll down a little bit? Thank you.
Mm-hmm. So we can form a triangle here. Notice that this length here is our x value, right? 2. And this value here is 3. So we could figure out, if we wanted to put this in polar form, we could figure out what this length is by Pythagorean Theorem. So if I wanted to call this r, I can say, well, then r is equal to the square root, or we had done before, r squared equals, in this case, 2 squared plus 3 squared. R squared equals 4 plus 9. So r squared is equal to 13. So r is equal to the square root of 13. So there's a formula here that z we can call this, oopsie. the magnitude. So the magnitude or modulus of z, spelled it wrong. And it's denoted, looks like absolute values of z, is the distance from the origin to the point xy. Okay, so this we can also denote as z. So the absolute value of z, or the magnitude of z, or modulus of z, can be written as the square root of squaring your x value plus squaring your y value, which is what we did here, just like we've been doing in the past by getting that length of our hypotenuse or our radius. So last two sections that we're going to look at in this book talks about vectors, and vectors are lines basically that have direction and they have length, magnitude. The conjugate of z is written as the following. So it looks like z with a horizontal line right above it. And it's equal to, remember the conjugate is just the sign change. So this would be x minus iy. Where again, z was equal to x plus iy. They show that z times the conjugate, well, if you multiplied x plus iy all times x minus iy, well, this is a difference of squares, right? And so we could just square our first term. This would give us back the same thing as x squared minus iy quantity squared. So y squared, but I squared is -1. So that's something you should remember. I squared equals -1. And so when I square that I get -1 plus, so this is going to make this a plus. So this is the same thing as x squared plus y squared, which notice is the same thing as this. So another way to write z, and I don't know why you would want to do this, but maybe you would, the magnitude of z, or the absolute value of z, is equal to the square root. Instead of writing x squared plus y squared, we can write it as z times its conjugate. Okay, so we want to be able to go back and forth between a complex number in rectangular form and a complex number rewritten into polar form. The reason we want to do this is because there's some tools that can make it a lot easier for us to do some math with the polar form versus the rectangular form. The rectangular form would take so much more work, where the polar form wouldn't take very long at all. And so we're going to come up with some of those things. So this is going to look familiar. So in polar form, we had, remember, x was equal to r cosine theta. Y was equal to r sine theta. And we kind of got those just by looking at what the relationship of sides are. For cosine theta was the adjacent over your hypotenuse, which is your r value. And then same idea for sine. So the polar form of a complex number is as follows. R, if it's greater than or equal to 0, and your value of theta is between and including 0, but not 2 pi, the complex number z equals x plus iy can be rewritten in polar form as z is equal to r cosine theta, that's your x value, plus I times r sine theta. So remember, the y value is like the imaginary part. So I times r sine theta. Notice we can factor out a r here. So we can say z is the same thing as r times cosine theta plus I sine theta. So let's just kind of look at just a generic case. So let's say that you have some point z is equal to x plus iy, and you plotted it. So you're plotting your real part, and then you're plotting your imaginary part, or real part, and go your imaginary. So let's say that you just plotted it and it happens to be right here. So we need to figure out what r is. Well, r, that's just the square root of squaring our legs, x squared plus y squared. We need to figure out what theta is. Well, we can figure out what theta is. If we're just given our x and y value and we didn't want to figure out what r is, we could look at it using tangent. We can use it whatever trig function you want to use, though, if we have ratios of sides. So, but theta is the same thing as, remember, tan theta is opposite y over x. And so taking the inverse tangent of both sides, so theta is tangent inverse of y over x. Z is called the argument. Oops, sorry. And notice that the z is equal to r. Or the absolute value of z is equal to r. Okay, so this book brings in something that it hasn't called it this in the other textbook. But you have Euler's formula. And it's just another way to write this. So if you have e raised to I times theta, this is the same thing as cosine theta plus I sine theta. And if you had e raised to the ri theta, this is equal to r times cosine theta plus I sine theta. So this is the exponential form of the complex number. So this is just a lot faster to write the e to I theta instead of cosine theta plus I sine theta. Textbook I was using before was calling it cis. So if you saw cis of 2 pi, this was saying that you were looking at cosine of 2 pi plus I sine of 2 pi. That's shorthand. Or this book is saying, well, we can rewrite this as e I to the 2 pi. So these are all just kind of notation, just two of them are shorthand of having to write this out. Okay, so let's look at this. Basically, we're doing the same thing we've been doing a lot, like at the beginning of the course, looking at the triangle, looking at angles. So let's say that you had the following. You have 1 minus root 3 I.
Professor,
Mm-hmm.
right on top of that, next to the 2 pi in parentheses, is that CIS?
Yes. And so this is just shorthand for writing out C for cosine. I meaning it's an imaginary number. And the S is the sine piece. So it's just a shorthand way to write this. So these are just shorthand. Of writing this whole thing out. So the following says plot each complex number in the complex plane and then write it in polar form and in exponential form. So it's going to want us to write it in this form, this cosine of the angle plus I sine of the angle. And it's going to want us to write it in the form of e raised to the r I theta. So first thing you guys want to do when you're doing these is graph it, and it told us to graph it. So this had the directions to graph. Rewrite the complex number in polar form. and exponential form. If you are looking at material on this, sometimes they call this imaginary number trigonometric form, putting it into what we're calling polar form. They're the same thing. Okay, so anyways, we're going to plot this. So our real part is 1, and our imaginary part is -√3. So our real part is 1. So we're going to go over 1 to the right, and our imaginary part is this -√3. So we're going to go down -√3. Sorry, I don't want to point there.
To get an accurate point, would we have to like punch that in the calculator if we didn't know, or can we just kind of plop it down somewhere?
You can just prop it down from there. Yeah, let's just do that. I know that square root of 3 is between square root of 1 and square root of 4. I think choose 2 perfect squares I know that sandwich this and are closest to it. So I know that square root of 1 is 1 and square root of 4 is 2. So I know my numbers between 1 and 2, and I'm just getting some sort of a guess. I don't really care too much. I'm just plotting it. So from there, we just graphed it. And so now we can figure out what theta is. And we can figure out what r is. So we have to figure out how much we're swiping around here. And we know that this value in here is 1. And this value right here is √3. So this value r is equal to the square root of 1 squared plus √3 squared. So this gives us 1 plus 3 underneath the radical, square root of 4, which is 2. So we now know what r is, and now we need to figure out what theta is. So theta is equal to tan inverse of y over x. Our y value is √3, all over our x value, which is 1. I think to myself, because I'm in quadrant 4, so I have to think about what quadrant I'm in. I think to myself, what value of tangent gives me positive √3 over 1 if I was like in quadrant 1 just to get my reference angle. And so that's 60 degrees, but these have to be in terms of real numbers, so radians. And so 60 degrees is pi thirds. And so theta is pi thirds, but we're following in quadrant 4. So our reference angle is pi thirds. And so here we have 2 pi minus pi thirds. And 2 pi minus pi thirds is, this is 6 pi, 5 pi thirds. So theta has to be 5 pi thirds. Okay. This is not our answer, but this is going to help us come up with our answer. So z can be written, all right, in polar form, again, as r times the quantity cosine theta plus I sine theta. So z is equal to, we figured out what r is 2. And theta was 5 pi thirds. So 2 times cosine pi thirds plus I sine 5 pi thirds. Okay, so you guys should know your angles. Cosine, fourth quadrant, positive. Cosine of pi thirds is 1/2. So this is 2 times 1/2. Sine, fourth quadrant, negative. So this is going to be minus I. Sine of 5 pi thirds. Sine of pi thirds is √3/2, but again, it was negative. I already put the negative out here, so I √3/2. So this is our polar form. Actually, I went backwards. Well, that's like a good check. This is our polar form right here. I went too far. I just evaluated it, kind of. This is not our polar form. This is our rectangular form or our complex number form. This is our polar form. Just notice that if we distribute our 2 right there, let's check it. If you distribute your 2 times 1/2, that gives us 1 minus, and if I distribute my 2 to this I times √3/2, those 2's cancel, and I get I √3. Notice that was the problem that we started with. Graph this. So we graphed it. The part B, find the polar form, which we did. It's the 2 times cosine 5 pi thirds plus I sine 5 pi thirds. You can have the 2 distributive if you wanted. And then the exponential form. This is where Z is equal to E raised to the I times R theta. So Z is equal to E, I, R in our case is 2. And our theta in this case is 5 pi thirds. So let me see. And they simplify. So we can say this is I 10 pi thirds. Pretty much, again, what we've been doing, just written a little bit differently. So let's look at one more. What if you were given just -2? So graph the complex number, plot the complex number in the complex plane. And then write it in polar form. Let's write the number in polar form and exponential form. So if we have Z is equal to -2, Notice that there's no imaginary part. So we could think of this as plus 0i. So actually the real numbers are a subset of the imaginary number system or complex number system. And so we can graph this. If we graph this, our real part is -2. So that is the horizontal axis is the real axis. So we're going to go over -2. And then I don't have any imaginary part, so I'm not going to go up or down. And so I have a point right here. So we can tell pretty easily what r is. R is this length. Well, this length here is 2. Theta, well, what would you have to do to swipe over here to your negative x-axis? Theta is just pi. So z is equal to r times cosine theta plus I sine theta. So z is equal to r, which is 2, all times cosine of pi plus I sine pi. If you evaluate that, you better get back just -2. And then rewriting it as z is equal to e r times I theta. Exponential form. This is e. R is 2. And then we have theta, which is pi. So 2 pi I. They tend to write the I in front of this piece. So I 2 pi. Yeah. Okay, so now you should be able to go backwards. If you were given what the value was in polar form or exponential form, you should be able to find it in the complex plane, rectangular form.
Professor?
Mm-hmm.
So then here where the exponential form was the e, the polar form was the one you have in the rectangle. And which one would be the
This is the polar form, the cosine theta plus I sine theta. And this is the exponential form, the Euler, the e raised to the I, ri theta.
Oh yeah, I just noticed it said graph in the complex form. I was looking for the complex.
Yeah. So the complex plane, yeah, and so this was our real and then the imaginary.
Okay, thank you.
Yeah. So going in a different direction. So let's say they gave it to you already and they gave it to you in polar form. And you want to write each complex number in rectangular form. So write each complex number in rectangular form. So if you have 4, all times cosine of pi halves plus I sine of pi halves. Pretty much just evaluating this. So this is the same thing. Let's say this is part A. As 4 all times Well, cosine of pi halves, that's getting me to the y-axis. Cosine is 0 on the y-axis, so this is 0. Plus I sine of pi halves. I know sine pi halves is 1. So this is going to equal 4 times 0, which is 0, plus 4 times I, which is 4i. We should have been able to graph this without converting it to 4i. If I was looking to graph this, we know what theta is and we know what r is. So we have theta is pi halves and r is 4. So if you look at that and you rotate pi halves, again, that gets me to the positive y-axis, and then go up 4. Notice if I graph 4i, rectangular, my real part is 0, my imaginary part is 4. I would just go up, same thing. Just kind of tying it back together. So let's say now it says, do the same thing, but this time your equation is so I'm trying to see if there's ones that we know. Okay. How about 2e I to the 5 pi 6?
Error.
I made an error. It didn't matter right here. It's back here where the Euler's form. We're gonna go back there. That r is not in the exponent. This r is out front of the e. So this is r times e to the I theta. So back over here, we're okay till we get to the exponential form. That r, which was 2, needs to go in front of our e. They might be equivalent. I don't have the proof. It says that you have to have more extensive math to be able to do the proof. But let's just follow the formula. So here, yeah, so our r value was 2. So r goes in front. So this should be z is equal to 2e to the I pi. Okay, so from this form, we know what r is. So r is 2. And our theta value is 5 pi 6. So I wanted us to get right each complex. Okay, so we know what this is. This is equal to I'm going to just rewrite it like this, cosine of 5 pi 6 plus I sine of 5 pi 6. So I have to think about what quadrant we are, 5 pi 6. My reference angle is pi 6. So this is equal to 2 times cosine of pi 6. Cosine of 30 degrees is root 3 over 2. Cosine is negative in quadrant 2. Plus I sine of 5 pi 6. Sine of 5 pi 6, that's 1/2, and it's positive in quadrant 2. We have a 2 out front here. So this was 1/2. Notice if you distribute your 2, your fractions go away. And so we're left with negative root 3 plus I.
How did you get the square root 3 over 2? You did the
So cosine of 5 pi 6. So these are those angles that you guys need to know. So cosine of 5 pi 6, and I got the 5 pi 6 by looking at the exponent. Reference angle, so cosine of 5 pi 6, my reference angle is pi 6. So pi 6, I have 3 fingers above, is cosine is above, so that's root 3 over 2. Second quadrant negative. Sine is below, so that's root 1 over 2. So kind of a great review at the end of the semester of what we went over at the beginning of the semester. So that was where, I said you guys are gonna be doing this over and over and over again with these triangles. These are the angles you got to really know and be able to come up with them pretty fast. And again, you're going to see that stuff in calculus. So knowing those angles or being able to derive them is going to be really helpful. Okay, so there's some rules with multiplication and division. We can use rules of these polar coordinates, polar equations to help us. Let's see where we're at. So we have some theorems. And it's for a product and quotient of complex numbers. So if you are multiplying, so let's say z sub 1 is equal to r, e, I, and let's call it r sub 1, theta sub 1 power. And z sub 2, this is equal to r sub 2, e, I raised to the theta sub 2 power. So if these are two complex numbers, then we can say the following. If we multiply z sub 1 times z sub 2, this is equal to Well, let's just rewrite it in the other form, the exponential form. So this is the same thing as r sub 1, ei to the theta sub 1, r sub 2, ei theta sub 2. Well, we can rewrite this using rules of exponents. So let's pull the r sub 1, r sub 2 out front. R sub 1 times r sub 2. This is the same thing as e to the I theta sub 1, e to the I theta sub 2. So remember rule, same base. These have the same base e. You add your exponents. And so this would be e to the I theta sub 1 plus I theta sub 2. Those are both complex numbers, so you can add them together. It's generic right now, so let's just factor that I out of the exponent. So that would be I times the quantity theta sub 1 plus theta sub 2 in that exponent. And so they leave it like that. So if we're multiplying, when it comes down to, if we're multiplying two complex numbers together, then basically we just have to multiply their r values together and then do e, I, and then add their thetas together. So this book is really big on this Euler's form. I'm used to it more in that complex, the polar form, where this would have been written as the same thing as z sub 1, z sub 2. It's the same thing as r sub 1 times r sub 2. This would be cosine of summing my angles, theta sub 1 plus theta sub 2, plus I sine theta sub 1, theta sub 2, theta sub 1 plus theta sub 2. I think putting it in this exponential form, it kind of proves why that formula comes out. And this is the same way of saying if we looked at z sub 1 and z sub 2 as being in the form of rectangular form of a complex number. So this would be x sub 1 plus I y sub 1 all times x sub 2 plus I y sub 2. So that's really helpful. If you were going to multiply, it actually comes out sometimes a lot faster than what you would have been if it was in rectangular form. Let's look at an example. So let's say you had z is equal to cosine of 2 pi thirds plus I sine of 2 pi thirds and they define W to be the complex number, cosine of 5 pi ninths plus I sine of 5 pi ninths. So find z times W and z divided by W. We haven't looked at that yet, and write each answer in polar form and exponential form. We're going to go polar form, exponential form, and rectangular form. Okay, so polar form, z times W. Basically, we look at our R value. Our R value, notice there's no number in front other than 1. So R sub 1 here is equal to 1. Our theta value, theta sub 1 for our first equation is equal to 2 pi thirds. R sub 2, again, it looks like my R value is 1 here. And my theta value is, theta sub 2 is 5 pi ninths. So this tells me to take my R values, 1 times 1, all times cosine, summing those angles. So cosine of, I'll come back to it, plus I sine and summing those angles. So we're taking 2 pi thirds, 2 pi thirds, and then plus 5 pi ninths. So this is equal to 1 cosine. We need a common denominator. Common denominator would be 9. So if we multiply this by 3 over 3, so this is 6 pi ninths plus 5 pi ninths is 11 pi ninths. And so plus I sine of 11 pi ninths. So that's polar form, exponential form. R is 1. 1 times 1, which is 1. E, I to the theta. And we summed our values. So that would be 11 pi ninths.
Professor, for the R, you had 1 because there was no number in front of like the equation.
Yeah, so if this had been 2 cosine of 2 pi thirds for z plus I, or 2I sine of 2 pi thirds, I would have known my R value for that z would have been 2. But each coefficient in front of my cosine and my sine are 1. Same thing with W, or sometimes it will be factored out, but if there's nothing I can pull out. So my R value in each case was 1. We actually can't do this one without the calculator, so I'm not going to put it in rectangular form. So let's look at division. Division is almost identical. We can think of it with, say, z is equal to x sub 1 plus I, y sub 1, and w, let's say, is x sub 2 plus I, y sub 2. Division, if we think about it, then this is the same thing as e to the, let's look at z divided by w. If we put this in exponential form, this is e, or r sub 1, e pi theta sub 1, all over r sub 2, e I theta sub 2. Remember rules of exponents, same base. We have the same base of e. Then we can subtract our exponents. So if we want to divide complex numbers, we're basically just dividing the r value in the numerator by the r value in the denominator. And then times e, subtract our exponent. So this would be I theta sub 1. I can factor it out, minus the one on the bottom, theta sub 2. Or polar form, r sub 1 all over r sub 2, that cosine, it would be the difference of the angle, the one on top minus the one on bottom. I sine of the difference of that angle. theta sub 1 minus theta sub 2. So this is division theorem.
Can you label again which type of equation was like polar or?
Yeah,
I got a little lost.
I know they kind of interchange things too. Like I said, sometimes some books call this trigonometric polar form, but this is the polar form. So the polar form has the theta and the r in it, kind of like when we were thinking of points in the form of r and theta. Think of the e, you have exponents, so that's the exponential form. And then the rectangular form is when you have x and y in it. This one's rectangular. Okay, how about I'm going to do an example, but it might be good just to take a break and then come back and do an example. And then I'll show you why these, especially the multiplication, is really helpful, or just raising things to powers. So for instance, if I had to take some complex number, x plus I, y, and I had to raise it to the 100th power, I had to multiply that out 100 times and distribute, that would take forever. Where if I used this theorem and I convert it into polar form, it would fall out like that in seconds, well, not seconds, but minutes, where we could do it by hand. So this is where converting things could be helpful in other circumstances. So let me pause the video and then let's take a break. Okay, so we're looking again at polar and exponential form of complex numbers and multiplying and dividing these numbers. If you were given the following example where z is equal to 1 minus I and w is equal to 1 minus root 3 I. So let's find z times w. So actually, let's do it in all three ways. So let's say that we had to do this the long way, where we wanted to look at what is z times w. So z times w, in the form that it gave us, is equal to 1 minus I, all times 1 minus root 3 times I. So we could distribute this out and simplify. And if we did this, we get 1 times 1 is 1. 1 times negative 3 root I is negative 3 root I. Negative 1 times I is negative I. And then negative I times negative root 3I. Negative times negative is positive, but I squared is negative 1, so that's another negative. So it's negative. And then just root 3. Let's just rewrite this where our real parts are together and our imaginary parts are together. And so our real parts are 1 minus root 3. And then our imaginary parts are negative root 3 minus I. So 1 minus root 3, that's my real part. And then I can factor in a negative in here. Oops, I forgot my root 3. Oh wait, this part of the I, root 3I. I can factor out a negative, and I can also factor out, I don't know why that does that because I never play that game. A negative and an I. So we have negative parentheses, square root 3 plus plus 1 I. So I just also want to show you this with graphing. So if we did 1 minus square root of 3, let me just give you a kind of an estimate where we would graph this complex number on the rectangular coordinate. So we have 1 minus square root of 3. That's going to give us negative 0.73. And then this is minus, so root 3 plus 1. .73 I. So if we graphed this, we go over about negative 0.73 and we would go down about negative 2.73. So it'd be about here. So now let's look at it using Euler's method or putting it in an exponential form and polar form with multiplying. So z is equal to 1 minus I. We want to convert this. So first thing we can do is we can graph it. So we want to graph z to find what our r value is and what theta is. So if we graph z, this is going over 1 and down 1. So I know this z value here is in the 4th quadrant. We know that this is 1 and this is 1. So if we use absolute value of z, which is the same thing as r, it's the square root of 1 squared plus 1 squared. So r is equal to the square root of 2. Theta, this is equal to tan inverse of opposite over adjacent, which is 1 over 1, which is 1. Where theta is contained in quadrant 4. So this would be pi fourths, but in quadrant 4, that's going to be 2 pi minus pi fourths. Is 7 pi fourths. Okay, so we can rewrite z. Z is equal to r times e to the I theta. So z in exponential form, our r value was root 2. Our e value is I theta, which was 7 pi fourths. So we want to do the same thing for w. So w is given to us to be one minus I root 3. So if we graph this, we're going to go over 1 and we're going to go down root 3. So looking at this, we have what? We have that r is equal to the square root of root 3 squared, which is 3, plus 1 squared, which is 1. So r is equal to square root of 4, which is 2. Theta is tan inverse of opposite, which is root 3 all over 1. Theta is contained in quadrant 4 here. So looking at this, this is going to give us, so that is 60 degrees pi thirds, 7 pi thirds. Nope, 5 pi thirds.
Can you do the thing where you like explain what you did to get to 5 pi thirds? I'm still struggling with that.
Yeah, so I have to think backwards. So I'm thinking backwards and I'm thinking to myself, what angle gives me tangent? So tangent of what is equal to root 3? So I'm thinking first of all in the first quadrant. And so I know tangent is either going to get spit back for 30 degrees or 60 degrees, root 3 or root 3 over 3. So then I remember that root 3 over 3, that was the 30 degrees. So all this is going on in my head at once. So that has to be the 60 degrees. So 60 degrees I'm converting into radians, which is pi thirds. And so I know my reference angle is pi thirds. And then I know that because I graphed this, I'm down in the fourth quadrant. I have to figure out what this pi thirds is in here. And so I know that a full rotation would have given me 2 pi. And so I have 2 pi minus my reference angle of pi thirds. And so then I have to get a common denominator. So this is a 6 pi thirds minus a 1 pi thirds, which is a 5 pi thirds. And so that would give me my angle theta here. For W. Does that make sense?
Yes, thank you.
So this is what we have. And R we said was, I know we said was 2. I just can't see where we said it. Or maybe we didn't. Yeah, it is right here. So we can rewrite W now in terms of an exponential form if we want. So W here is equal to R, which we found was 2. E to the I theta, which we found to be 5 pi thirds. So now I'm taking my Z times my W. So Z times W in exponential form. I'm going to get my root 2. That's my R value. Then I'm going to do my R value of W. E to the R, sorry, not R, I theta. So I 7 pi fourths. And this is EI to the 5 pi thirds. So my R value for W was 2. So R times R. And my EI to my theta, which was 5 pi thirds. So we get ZW, the product is equal to 2 root 2 E, and now we can just add our exponents. Well, I need a common denominator. My LCD for 4 and 3 would be 12. So I'm going to have to multiply this 7 pi, what was that? Is that a 7 pi fourths by 3 over 3? And I have to multiply this 5 pi thirds by 4 over 4. So this gives me 12 pi, sorry, this gives me 2 times 3, which is 6 pi 12ths plus 20 pi 12ths. So 6 pi plus 20 pi, that's 26 pi 12ths. Well, this is the same thing as, well, 12 goes into 26 twice. And then we have a remainder of 2 over 12 pi.
Excuse me, Professor.
Mhm.
I think that was a 7 pi over
Yes.
4.
It was, you're right. Thank you. Here it kind of looks like a, thank you, 7 pi over 4. So this would have been a 7. Well, no, it would have been a 7 times a 3, which would have been a 21. Even gives us bigger. Plus the 20, so that's 41 over 12. So 41 pi over 12. So it goes in there 3 times. So that is 3 pi plus a remainder. A remainder, that's 36. That gets me 5 pi 12ths. You know, the reason I'm doing this, I'm wondering if we can leave it like this, but the reason I'm doing this is because it might want theta to be between 0 and 2 pi, although it didn't say that. Because remember, this is going to be rotating, and so we could get back to the same thing. We can simplify it. So maybe we can do this. Actually, let's just put it up here, 41 pi over 12. And then I'm just curious on how they wrote it. And since it's not right by it, I have to look it up in the back. So it looks like that we're getting that theta value. We want to be between 0 and 2 pi. So the equivalent value that would get us there. Find an equivalent angle. Okay, so I would want to start subtracting 2 pi, because I know that 1 revolution is 2 pi. So if I subtract 2 pi, well, let's get this in a common denominator. So let's do this as 12 over 12. So I have 41 pi 12ths minus 24 pi 12ths. So 41 minus 24, that gives me 17 pi 12ths.
Would this be similar to like if you had converted it to degrees and you know how you subtract the 360 over and over?
Yep, exactly. But because this was in radians, I was doing it subtracting 2 pi. So if this had been less than, or if this had been more than 2 pi, here I would have done subtract 2 pi again, because I would have done more than 1 full revolution. So this went 1 revolution plus 17 pi 12ths. And so 17 pi 12ths, that was terminology, that was the terminal angle. So this was an angle that was equivalent, it would get us into the same spot as the 41 pi 12ths. And so we can rewrite this z times w as 2 root 2 e to the 17, my eye should be in there, 17 pi 12ths I. So this would have given us the same thing pretty much as if we had written this in trigonometric form. Basically, we did all the work. We figured out what r was. Trigonometric form, this is where you're going to have your r's times r, so 2 times root 2. Cosine of the angle, same idea. We would have to get it down to this angle between 0 and 2 pi, so 17 pi 12ths plus I sine of 17 pi 12ths. So 17 pi 12ths. I was trying to do this to show you guys back here that we're going to, if we looked at this now, 2 root 2, that we would get at the same spot that we had over here. Back at where we had started, actually over here. But we're running out of time, so I'm not going to do that. I'm just going to follow what they wanted us to do. So now we wanted to look at z divided by w. Okay, so again, let's just rewrite what z is. So z was, actually I have it right here in my book without scrolling. Z was 1 minus I all over 1 minus root 3i. Z, we already found that r is equal to, that one was the root 2. W, r was equal to 2. Theta for z we found to be, I already did that work. It was 5 pi, no, 7 pi fourths and 5 pi thirds. So exponential form, we would have our r value, which is root 2, e raised to the 7 pi fourths I, all divided by 2 e to the 5 pi thirds I. Using rules of exponents, we have division. So this is root 2 over 2 e, and then we're going to subtract our exponents. Again, we're going to need a common denominator in order to subtract these. So let's multiply this one by 3 over 3 and this one by 4 over 4. So that was a 21 pi 12ths minus a 20 pi 12ths. And then we still have our I. So that's 1 pi 12ths, or pi 12ths I. So polar form, we have our root 2 all over 2. Cosine, well, if we subtract those two angles, well, we already did the work here. So subtracting the two angles, we would have pi 12ths plus I sine of pi 12ths. Okay, so we get a theorem, de Moivre's theorem. De Moivre's theorem says that if you're going to raise something to a power, then we can use this kind of concept to get the following. So DE and then capital M OIVRE apostrophe S theorem. So if you have R e to the I theta, oops, that's not his theorem, sorry. If Z is equal to R e to the I theta is a complex number, so remember, real numbers are a subset of the complex numbers. So real numbers are actually complex numbers too. So if Z equals R e to the I theta is a complex number, then if we raise Z to the nth power, this is going to equal R raised to the nth power, E raised to the, well, if you raise an exponent, if you have an exponential piece, power raised to power is multiplication. So if I raise this E raised to I theta, and that's all raised to the nth power, then that's just going to be multiplied. So it's going to give us I times n theta. Or if we were thinking of this in complex form, then we would have polar form, r to the nth cosine of n theta plus I sine of n times theta. Oops. Yeah. That's it. So there's another theorem that talks about how our complex numbers are periodic. So just like the polar numbers are periodic, there were different angles that can get us to the same spot, or different values of R that could get us to the same spot. So this theorem says that complex number is periodic, and R e to the I theta is equal to R e to the I, where we're adding 2 pi k to theta, where k is equal to an integer. Which we were talking about up in this last example, and how we got back up, or when it was above 2 pi. The angle was above 2 pi, we got it in between 0 and 2 pi. So if you have 1 minus I, and you're raising this to the 5th power, then we can look at de Moivre's theorem. So if I look at 1 minus I, it's like we do this one all the time. So this right here is 1. This right here is 1. We know that our radical is square root of 2, or our R value. And then looking at this, we had talked about tangent inverse of 1 was pi fourths in our first quadrant, but down here, so 2 pi, so that's 8 pi, no wait, 12 pi minus 1, that's 11 pi fourths. Theta equals 11 pi fourths. And so if z is equal to 1 minus I, then z to the 5th is equal to square root of 2 raised to the 5th power, r to the 5th, e, I, and n times our n value, what power we're doing is 5 times 11 pi fourths. This is where I don't know how much they want you to pull out, because really the 5th root, or the square root of 2 raised to the 5th power, there's things that we can pull out of that radical. This is the root 2 raised to the 5th, e I to the 55 pi all over 4. And that's way bigger than so this is going to go around a lot of different times. And so we need to convert this. So we want to convert this between 0 and 2 pi. So I'm going to stop there. I'll look into how they actually have it, but we're pretty much out of time for class. And then if we want, we can pick up and I'll give you what the simplified version is of that. The other thing with this section though is finding roots. So having equations and then using this to find the zeros of polynomials. Okay. So let me stop.